Hello, Professor Yang. Hello, everyone. I'm Zhang, and today I'm very excited to present my final project for the computational chemistry. And my presentation title is Machine Learning for Prediction Organic Redox Potentials. And in this study, I will explore how combining traditional molecular descriptors with quantum chemical features, especially HOMO and NUMO energies, can enhance the predictive power of machine learning models and finally achieve a very wonderful accuracy. And my presentation is structured into five main sections. First, I will discuss the background and the challenge of the redox potential prediction. And then I will detail the feature engineering process and the various machine learning models we test. Finally, I will highlight the revolutionary impact of homonormal features on our prediction results and conclude with our key findings. And okay, let's start. And first with why. Redox potential is a fundamental measure of a molecule's ability to gain or lose electrons. And this property is the cornerstone for designing advanced batteries, organic flow cells, or drug metabolism. And however, we face a major challenge. While experimental measurements are very costly and slow, and for the density function theory calculation, though they are very accurate, but they are very computationally intensive for screening thousands of molecules. And our goal is to develop a machine learning pipeline that provides fast DFT level accuracy in a fraction of the time. And to solve this, we designed a comprehensive machine learning pipeline. This workflow involves data preparation, feature extraction, model selection, and rigorous validation. And our primary objective is to see if we can use structured descriptors and quantum mechanic features to replicate high-level DFT results. And our data set consists of 159 diverse organic molecules, including 4 different groups. And to provide high-quality tables for our machine learning, we perform DFT calculation using RCA at a very high level. We calculate the Gibbs-free energy for the neutral oxidities and the reduced states, as shown in the formula. We then convert these energies into standard potentials. And as we all know, the quality of any machine learning model depends on its data. And our data sets consist of 159 diverse organic molecules from 4 distinct families. And for every molecule, we compute 3 states: ground, oxidized, and reduced. And we utilize high accuracy DFT calculations at the PBEO, PBE0, DF2, TZVPP level to establish our target labels, the oxidation and the reduction potentials, and using the standard Gibbs free energy difference formula shown in the above slide. And our initial approach relied on 2 standard classes of molecular descriptors and automatically generated from the molecular structures. And the one is the Morgan fingerprint. It accounts 512 features. And the second is RDKit 2D descriptors, and it has 15 features. And this feature set provides a very comprehensive description of the molecular structures and the basic properties, and forming the basis for our baseline models. And for our method, we evaluate 5 standard regression models from the simple linear regression as our baseline and the ridge regression for our regularization and the support vector regression for non-linear patterns and the random forest as an example approach, and the k-nearest neighbors for similarity-based learning. And to ensure these models perform optimally, and we use the grid search CV for systematically hyperparameter tuning, and 5-volt cross-validation to prevent overfitting. And this is hyperparameter optimization for each models. And let's take a closer look at the optimization for the support vector regression. And we conduct a comprehensive grid search and testing 35 combination of C and gamma as per the project requirements. We explored a vast range for C from 1 all the way to 1 mini, and this exhaustive search allows us to find the precise balance between the model complexity and the array minimization. And finally, we choose these parameter combinations. And initially, we trained the models using the 527 structure and the physicochemical features, such as the Morgan fingerprints and the RDKit descriptors. The results were encouraging but very limited. Our best model, the ridge regression, achieved an R squared of 0.84. However, the mean absolute error MAE was only 1.33 volts. And in chemistry terms, 1.3 volts error is very significant for practical screening and representing a 10 to 15% relative error. And this suggests that the structure features unknown are not enough to capture the complex electronic nature of the redox reactions. And this leads us to a critical hypothesis. Structure features describe what a molecule is, but they don't describe its electronic behavior. And in redox chemistry, oxidation is the removal of an electron from the HOMO, and the reduction is the addition of an electron to the LUMO. We realize that these frontier orbital energies are the direct physical descriptors of the electron transfer, the very essence of what we are trying to predict. And to incorporate these physical-based insights, we perform supplementary DFT calculation to extract the HOMO and LUMO energy for all 159 ground state structures. And we used the PBE zero functional and DEF2 TZVPP basis set. And by extracting these specific energy levels, we moved from a purely black box structure model to a physics-informed machine learning models. And here are the results from the HOMO-LUMO calculations. And the impact of the adding just these three features, HOMO, LUMO, and their gap, was nothing short of the revolutionary. Despite this feature making up less than only 1% of the total input data, they fundamentally changed how the models perceive the chemical space. And when we returned our best model, the ridge regression, with the enriched feature set, the performance skyrocketed. The R-square value reached a near perfect 0.996, and the MAE dropped from the 1.33 volt to the just only 0.067 volt, and this is a 95% reduction in error. And our model transformed from a rough estimator into a high precision instrument capable of replicating DFT accuracy at a very high speed. And this improvement wasn't limited to just one algorithm. As shown in the chart, every single model, even simple linear regression, saw massive performance boost once performed by quantum chemistry. And our final recommendation is a ridge regression. It offers the best balance of the R-squared near minimal MAE and very high speed and very excellent interpretability. And to conclude, this project is This drawing demonstrates three vital points. First, machine learning can predict results potential with meaningful level accuracy. And the second, correct feature engineering is more important than model complexity. And the third, physics-informed features like homonormal energies are indispensable for chemical property prediction. And our model is now ready for high-throughput screening of the large molecule libraries. And thank you very much for your attention. And I hope this presentation demonstrated the power of combining computational chemistry with machine learning. And if you have any question or would like to discuss the methodology further, please feel free to reach out via my HKU email. And I would like to express my sincere gratitude to Professor Yang Jun for his engaging lectures and invaluable guidance. And I also acknowledge using the AI tools for the code development and using the NotebookLM for the presentation structuring. And I also would like to acknowledge using the ORCA and the Scikit-learn that assisted in the development and the structure of this project. And for those interested in the underlying data, this slide provides a statically summary of the orbital energies across the four chemical families. And we observed a significant range in HOMO energies, particularly between the first two and the last two series, which provides a necessary variance for our machine learning model to learn effectively. And the following slides contain the detailed regression plots and the error distribution for each model for your reference. And this is a ridge regression, SVR, KKN, RF, and the linear regression. And for your reference, I would like to show you more about this project. Okay, oh no, this cannot open. We can find from this. And here are some of my preparation documents for this presentation. And these are helped by the Copilot. And here are using some of my using images. And I would like to show you my code. And this code is for the machine learning feature extractions. And let me show you as detail. And for the RDKit features, let's run it. It's very fast. And this is the machine learning train models without the homonormal features. And this is another data, train linear regression, train different models, and the evaluate models. Okay, let's run it. Okay, it's run without errors. And this is the code for the adding homonormal features. We're adding the homonormal feature into this. Okay, and you can see from the results. And this is the model comparison with and without the homonormal features. This is before and after. And I would like to show you more about it. Okay. And this is my calculate format normal features from the ORCA calculations. This is 159. It has 159 features, monikers. And here are some of rendition plots. And as you can see, all of these projects was done by myself with the help with artificial intelligence tools such as the VS Code, Copilot, and the NotebookLM. And that's all. Thank you for your listening.